Hi friends, welcome to follow up. Let's have a look at today's daily challenge problem. Problem 111, minimum depth of a banana tree. This problem is an easy one, so the purpose of this video is to present three versions of solutions based either on recursion or iterative formats. First, let's look at the short statement. So here we are given a binary tree. We want to find its minimum depth. So the definition for minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. So a leaf node is a node with no children. So here we have two examples. Let's look at example 1. So we have actually three root to leaf paths. So one is 3, 9. One is 3, 20, 15, and the other is 3, 27. So the three passes have length or the number of nodes 2, 3, 3. So we return 2 for this problem. So similarly, you can look at example 2. So the example 2 is like this. We have a root 2, and then the root have a left subtree 3. Then 3 have a left subtree 4, and 4 have a left subtree 5. And 5 have a right subtree 6. So all these are just the right subtrees, right? So the root to leaf nodes of 2, 3, 4, 5, 6 in the path. So we output 5. The constraints for the problem are the following. First, the number of nodes in the tree is in the range given by the closed interval 0 and 10 to the power 5th, and node values is bounded in absolute value by 1000. So with that said, basically we are ready to do the coding part because the logic is very simple. So for the first version, I'm going to use a recursion. So actually this problem we need to use some caution because we want to find the minimum or the shortest path from the root node down to the nearest leaf node, right? So let's first treat a base case, if not root. So in this case, we return 0. This is the for sure. So we regard this as a base case or a stop condition. So now let's look at the other case. If not root left, right? So in this case, what we are going to return is 1, right? The root node plus the shortest path from the right subtree out for the right subtree, right? That is self min path depth, so root right. So similarly, if not root right, so we're going to return 1 plus the shortest path for the left subtree or the mean depth for the left subtree. And then otherwise, so we're going to return, so if there's no left subtree and no right subtree, so it means that this is just a single node root. So we're going to return 1 plus. So this is the one case, and the other case, all the other case is we have both left subtree and the right subtree. So we're going to return the mean, right? So that's the mean in the definition or in the requirement, right? So we're going to copy this to part. And let's copy also this part. Yeah, this actually forms one solution format. So this solution format is in recursion, right? So this is one case for the base case. So because these two if blocks are very special because there's no left subtree or right subtree. We need to extend by 1, then do the min depth for the corresponding right subtree or left subtree. And if the root have both left subtree and right subtree, so we're going to find the min depth, then extending by the root is adding 1. So with that said, let's first make a test. It passes the first example. Now let's test the second example because second example is very special. It just has extended to the right? Yeah, it passes the second one. Now let's look at the generic case. it passes all the generic cases. So this is the one solution, which is actually very intuitive. And basically, you can think we transform or translate this definition into code format. So let's copy this function signature and mark this one as solution v1. So now let's look at another solution format. So for another solution format, I'm going to use an iterative format, right? So this is to digest the detail. So for this, first I'm going to do this, if not root, right? So we just return 0, because this is the base case. Next, we're going to do traversal. Then when we do traversal, we can mark the labels, right? So then actually we can find all the leaves and their corresponding levels. So if we starting the level from 1, so for example 1, 2, so this will, the last level for the shortest path would be the return we want, right? So this way, actually we did some extra work. We found all the passes, right? We traverse the whole tree, but this is the one way. Let's do it. So first, I'm going to initialize a result. So because here the number of nodes is at most 10 to the power 5, so this is the largest possible depth, right? Let's initialize like this, or you can pick larger ones as you like. It does not matter. And then we're going to initialize a stack. So you can do breadth first based, or you do depth first based. So here we are doing depth first based. So we're going to use a root, and this level is 1, right? So in other words, what we store here is node and its level. So starting from using while indexing. So next, basically is a standard while loop for traversal. While s, so we're going to have node and level. It's s pop, right? Then we're going to see if the node is a leaf node. So node left or node right. So if we negate this expression, it means that the node currently we are looking at is a leaf node. So in this case, we can update the result. So here we are using min function, right? Because we are going to find the shortest path or minimum depth. So this is the result, previous state, and the current level, right? And otherwise, so this node is not leaf. So then we can consider add the corresponding left subtree and right subtree to the stack. So let's check the right subtree first. If node right. So here I'm going to append node right, and the corresponding level is incremented by 1, right? Then let's check left subtree, right? So I'm going to copy this part, and then so here is left. So here this true if the order is not of importance. However, if you do specific order traversal, like say pre-order traversal, so you need to first put right and then left. So now with that done, so what we are going to do is to return the final state of result. So this forms the second solution format. Actually for this one, because we traverse all the tree, so we actually find all the root to leaf path, and then we compare the leaf levels, and then we choose the min one. So this is the here. Min here corresponding to min here, corresponding to min here. So before we make any comments, let's first do a test. Yeah, it passes the second example. Now let's look at the first example. Yeah, it passes the first example. Now let's look at generic case. Yeah, it passes all the generic cases, but a little bit slow. So now let's improve this version. So I'm going to copy this part, and then I'm going to put it here, and I'm going to call this one version v2. And for this one, it's still iterative, but we want to avoid to examine all the root to leaf passes. So in this way, I'm going to take into consideration of now. So originally, let's use so here let's use a queue. Let's see, collections deck. So here we just let's see, we put root and its level is 1, right? So here also you can use a queue behavior. Pop from left, here pop from 0, and then append from the tail. So it's going to be queue behavior. So now let's also practice this. So we are going to use a queue, right? And then what we are going to do is to notice that we didn't check if root is null or not, because we are going to write this logic in the code or in the traversal. Well, queue. So what we are going to do, we are going to have node and depth. That's going to be queue pop left. And then if node is none, right, then we continue, right? And otherwise, if not, say node left or node right. So in this case, the node is actually already a depth. It's already the shortest. It's also, and so this condition means that the node is a leaf node. And then because we are doing breadth first traversal or level order traversal, you can think of, and then this node, actually this leaf node corresponding to the shortest route to a leaf path. So in this case, we just need to return the depth. That's it. So otherwise, so basically we don't need to check, because here we take consideration of this now situation. Then if it's nothing returned, we just need to do append. So we're going to do node left and the level +1. So let's copy this line and make some modifications. This is right? And then if nothing has returned, it means that this is empty. So we're going to return 0. So this is another solution format. So because the third version actually, so because this is the shortest path, right? Shortest in the sense that we have minimum number of nodes in the path. So for problems related involves shortest path, we can consider a breadth first traversal. Notice that breadth first. So now in this case, you can think here this level 1 and this is level 2. So at level 2, you see, oh, this is the leaf node. Then we are already ready to return. So then we return. So this is the problem logic. But here is slightly different from the second version, is that so we didn't check if root is null or not at the very beginning, but we include this into absorb this special case into the whole code structure. So with that said, let's first make a test. Level. Let's see. Level is not defined. Level. Here depth. Let's change this to be a level. So now let's test depth. Yeah. So we need to make this level or depth. Use the same variable consistently, right? Let's run this. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So I would say for this 3 versions of solution, so this one is our recursion, which basically suit the data structure, because tree data structure is essentially a recursive data structure. So this is the first one. And the third version actually is also natural for this problem, because here it involves shortest path. We can first consider depth breadth first based traversal. So this is the version 3. Well, for version 2, so we are actually practicing traversal. This is the depth based. So in writing into this solution format actually is corresponding to pre-ordered traversal of binary tree. So this is good for understanding the problem details. With that said, basically That's about it for this video. Thank you.